Hi everybody, the purpose of this video is to go over section 4 of chapter 8, and in this video we are going to talk about vectors from an algebraic perspective. First we're going to introduce to you the algebraic interpretation of vectors. We are going to use that interpretation to do various vector operations such as addition, subtraction, and scalar multiplication. We are going to talk about how to express vectors in terms of a new vector or a new class of vectors called a unit vector. And then we will introduce the dot product and show you how you can use the dot product to determine the angle between two vectors. Okay, so you're all familiar with the geometric interpretation of the vector, and that happens to be an arrow which has a certain magnitude and a certain direction relative to some frame of reference. In this case, it's going to be the positive x-axis. And we call this a position vector. Well, we can also express this as an ordered pair. However, this ordered pair is not going to be surrounded by parentheses. It's going to be surrounded by angled braces, which you actually see right here. And it will have two components. The first component will be the horizontal component, which is A. So that right there is the horizontal component, as is that. And the second component, which is B, is called the vertical component, which describes the height of the vector. And the angle between the x-axis and this position vector is called the direction angle. So this right here is our algebraic representation for our vector. Okay, from this algebraic interpretation, we can actually determine the magnitude of the vector, i.e. this length, through the properties of the right triangle and the Pythagorean theorem. Essentially, this particular length is going to be the square root of the sum of the square of this particular leg and that particular leg, and that will give us the magnitude of u. The direction angle theta is that angle which satisfies this relationship. The tangent of theta being equal to the b, the tangent of theta will be equal to the b over a, i.e. the opposite over the adjacent, obviously for the case when a is not equal to 0. Okay, even though the tangent theta actually is equal to this ratio, we have to be careful when finding theta because we actually have to pay close attention to the quadrant of the position vector. Why? Well, if we want to find the value of theta, obviously what we're going to do is we are going to compute the arctangent of b over a. And that is going to produce for us a value in the range of negative pi over 2 to pi over 2, which is great if the vector resides in quadrant 1 or quadrant 4. What if the vector resides in quadrant 2? Well, then you're going to get a negative value from the arctangent, and what you're going to need to do is, whatever that value is, you are going to want to add 180 to it to get the correct angle. And if the angle is in quadrant 3, you're going to get a positive value for arctangent, and once again you will need to add 180 to actually get the correct angle. And we can actually illustrate that in an example. Oh, and by the way, here it is. So here we want to find the magnitude and the direction angle for the vector negative 5, 4. So that's going to have a horizontal component of negative 5 and a vertical component of 4. And notice that this vector resides in quadrant 2. So theta is going to be some number that is greater than 90 degrees and less than 180 degrees. Okay, and we'll deal with theta in just a second. What about its magnitude? Well, once again, we can use the Pythagorean theorem to figure out the magnitude. The magnitude of u is going to be equal to the square root of negative 5 squared plus 4 squared, and that will be the square root of 25 plus 16, which will give us the square root of 41. And if we're looking for an exact answer, that is the best we can do because 41 is a prime number. Okay, well, what about theta? Well, we know that the tangent of theta is equal to, it's going to be equal to negative 4, negative 4 over 5, or once again, the opposite is 4, but the adjacent is negative 5, so it'll give you the exact same thing. However, the arctangent of that value is going to be equal to negative 38.66 degrees, which, by the way, is this angle right here. Okay, that's not the angle we want. To get the angle we want, we actually need to take this value and add 180 degrees to it. So theta, in this particular case, since it is in quadrant 2, we can find it by taking this value and adding 180 to it, plus 180. And that will give us 141.34 degrees. And if you were interested in to the 10th of a degree, which we are, this will be 141.3. So here now we have the magnitude of u and the angle of u. But notice we were very careful in making sure that we mapped our arctangent result to the right quadrant. Okay, so suppose that you actually have, suppose you have a vector and you're given its magnitude, so you're given this length, and you're given the angle. How can you find the horizontal and vertical components? Well, remember, the cosine of theta is going to be equal to the adjacent side, which is a, divided by the hypotenuse, which is the magnitude of u. So solving for a, this is what you get. Similarly, the sine of theta is going to be equal to the opposite, which is b, divided by the hypotenuse, which is the magnitude of u. And if you solve for b, you get this. So that's how you find your horizontal and vertical components. And then to express your vector in algebraic form, you just take those values and put it in this format, and you are good to go. And that is what we are going to do here. So here we have a vector whose magnitude is 14.5 and its direction is 220 degrees. And we want to figure out its horizontal and vertical components. Well, the horizontal component, which is you will call A, is going to be equal to its magnitude, which is 14.5, times the cosine of its angle, which is 220 degrees. And that will be equal to negative 11.11 degrees. And this, negative 11.11, which will round to, well, negative 11.1 if we are interested in only one decimal. Similarly, b, that will be equal to 14.5 times the sine of 220 degrees, and that will be equal to negative 9.32, which rounds to negative 9.3. And that kind of makes sense because we should have a negative x, we should have a negative y. And if that's the case, we can express v algebraically as negative 11.1 and negative 9.3. And just like numbers, we can do vector operations. And we have talked about vector addition from a geometric perspective. Here it is from an algebraic perspective. If you have a vector AB, where the horizontal component is A and the vertical component is B, and you want to add CD to it, well, that's just going to be the sum of their components. So the horizontal component of the resultant will be A plus C, and the horizontal component of the vertical component will be B plus D. If you're going to multiply a vector by a real number, well, that is just the same as multiplying each component by that number. So K times the vector A. The vector AB is not going to be nothing more than k times A for the horizontal component and k times B for the vertical component. Once again, every vector has an opposite. We actually discussed that in our last class, in our last section, and it still applies here since we're still dealing with vectors. And how do we know if a vector has the opposite? Because then each component will be the opposite of the original, will be the opposite of the component in the original vector. So U has components AB, negative U will have components negative A, negative B, and it makes sense because if you sum them, you will get the zero vector as you would expect. Vector subtraction is the exact same thing as vector addition, where the second vector is the opposite vector. So AC minus CD is the same thing as AC plus the opposite of CD. And if you actually and if you actually perform scalar multiplication here with the implied -1 and then do vector addition, you're going to have a minus c for the horizontal component and b minus d for the vertical component. Okay, with that, let's do a few examples. So here we want to add u and v. Well, that is going to be the addition of the vector 6, -3 to the vector -14, 8. And that will be equal to, for the horizontal component, 6 minus 14. For the vertical component, -3 plus 8. Got to use the right bracket there. And that will give us -8 for the horizontal component, and then +5 for the vertical component. What about scalar multiplication? Well, this is going to be equal to 1/2 times 6 comma -3. That will be equal to the vector 1/2 times 6, and then in the vertical component that'll be 1/2 times -3. That will give us the new vector 3 comma -3/2. And then finally here, well, here we have subtraction of one vector with a scaled version of another vector. So this will be u. No, we already have u. This will be 6 comma -3 minus 2 times the vector -14 and 8. And we want to use the same order of operations that we have done for number systems. Specifically, we want to do the multiplication first. So if we do, we will have 6 -3, that doesn't change, minus 2 times 14, which is -28, and then for the vertical side, 2 times 8, which is 16. Okay, then that will give us, for the horizontal component, 6 minus -28. And then for the vertical component, we will have -3 minus 16. And then for the horizontal component, 6 minus -28, that's 6 plus 28, or 34. And then for the vertical component, that will be -19. Now, every vector can be expressed in terms of a unit vector. Well, that is great. What the heck is a unit vector? Well, these are unit vectors. Basically, unit vectors have a magnitude of 1, and then they have a particular direction. The two most common unit vectors are the unit vectors I and j. This is the unit vector I. This is the unit vector j. Okay? Notice that they both have the magnitude of 1, and they both have completely different directions. As a matter of fact, the directions happen to be orthogonal, or opposite. The algebraic representation for I is 1, 0, so there it is. The algebraic representation for j is 0, 1. Notice that these two unit vectors are orthogonal. As a matter of fact, it turns out that I dotted with j, and we'll talk about that just in a second, is equal to 0. As a consequence, it also turns out that any vector on the Cartesian plane can be expressed in terms of these unit vectors. For example, here's the vector 2, 4. We can write that as 4 times I. Okay, here's 4 times I, plus 2 times j. Here's 2 times j. And if we add it, and the sum of those two vectors is right here, which is 4i plus 2j. On the Cartesian plane, we can actually, we say that these unit vectors form an orthonormal basis for any array on the for any vector on the Cartesian plane. What specifically does that mean? Well, the ortho part in orthonormal means that these vectors are orthogonal. So ortho kind of implies orthogonal, which implies that which is a nice word. We're just saying that they form right angles to each other, and that their dot product, which we'll discuss in just a second, is equal to 0. Normal means that they have a magnitude of 1. Okay. And basis means that they span the entire plane, which is a beautiful way of saying that any vector on this plane can be represented by a linear combination of these two vectors. Okay, so I said a lot about dot product. What is a dot product? Well, first thing is a dot product between two vectors is a real number. It's not a vector. And a dot product is defined as follows. If we let u be equal to ab and v be equal to cd, the dot product of u and v is going to be the product of the horizontal components, or the first component, plus the product of the second component. And that is primarily the reason why that I, the unit vector I, dotted with the unit vector j, which is 1, 0, dotted with 0, 1, 1, is equal to, well, 0 times 1 plus 1 times 0, which is 0, which is why they're equal to 0. And once again, the dot product of two vectors is the sum of the product of their first components, the horizontal component, and the product of the second component, or the vertical components. So let's go ahead and compute a dot product of a vector. Here we have the vector -5, 2. We're going to dot it with the vector -2, -4. And what is that? Well, it's going to be the product of the first components, which is going to be -5 times -2, plus the product of their second components, which is going to be +2, -4. And then that will be equal to 10 minus 8, which is equal to 2. So that's all there is to it. Here are some of the properties of a dot product. The first one is that the dot product is commutative. The second one is that the distributive laws also apply to the dot product. So the distributive law in this direction, the sum of two vectors dotted with a third, is going to be the sum of the two dot products. And it's also distributive in the other direction. If you dot any vector as 0, you will get 0. If you dot any vector with a scaled version of another vector, then that scale can be outside the grouping symbol or actually grouped with the second vector. And if you dot a vector with itself, you have the magnitude squared of that particular vector. And notice that a dot product can either be positive, 0, or negative. Okay, the last thing we want to talk about is the angle between two vectors. You can actually use the dot product to determine the angle between two vectors. And I am going to prove that to you. I know you're really looking forward to that. So let's start off by drawing two vectors. Let's let the first vector be u. So here is my vector u. And here is my vector v. And of course there will be an angle between those two vectors. We're going to call that angle theta. Well, the difference between these two vectors is going to be the vector in this particular direction. And this is the vector u minus v. So here are the geometrical representations for the vector u, v, and u minus v. Now, algebraically, we can describe u as having components a for the horizontal component and b for the vertical component. Furthermore, we can describe v algebraically as c comma d, where c is the horizontal component and d is the vertical component. Well, if that's the case, then we can describe u minus v as a vector whose horizontal component is a minus c and whose vertical component is b minus d. Okay, now notice here we have two sides, and we know the magnitude of those two sides, with an angle in between them. So we can actually use the law of cosines to relate the magnitude squared of u minus v to the magnitude of squared of u, the magnitude squared of v, and the angle in between them. So with the law of cosines, we have that the magnitude of u minus v squared is going to be equal to the magnitude of u squared plus the magnitude of v squared minus 2 times the product of the magnitudes of u and v times the cosine of the angle between them. Okay, now what we want to do now is substitute or express this term and these two terms in terms of their algebraic components. So the magnitude of u minus v squared is going to be equal to a minus c squared plus b minus d, the entire thing squared. Okay, that will be equal to, what's the magnitude of u squared? Well, that's going to be a squared plus b squared, or what's the magnitude of the squared of u? And what is the magnitude squared of v? Well, that's going to be equal to c squared plus d squared. And then we're going to have minus 2, and I don't want to mess with these because I need to have those my final formula, or my final expression. So we're going to have the magnitude of u times the magnitude of v times cosine of theta. All right, now let's go ahead and expand these two terms, which we can easily do. And if we do, we will have a squared minus 2ac plus c squared. Then over here, we're going to have plus b squared minus 2bd plus d squared. And that will be equal to a squared plus b squared plus c squared plus d squared minus 2, the absolute value of u, times the absolute value of v times the cosine of theta. All right, now notice we have lots of stuff that we can cancel. So let's cancel some stuff out here. Notice I have an a squared on both sides, they're gone. I have a b squared on both sides, they're gone, as is the c squared and the d squared. And that will give us negative 2 times ac minus 2 times bd is equal to minus 2 times the magnitude of u times the magnitude of v times cosine theta. And notice that we have a common factor of negative 2 that we can get rid of, or a common term of negative 2. So we can cancel that out here, and these an implied plus sign there, and cancel that out there. And then we're going to have ac minus plus bd is equal to the magnitude of u times the magnitude of v times cosine theta. Now remember that u dot v is going to be equal to the product of their first components, a times c, plus the product of their second components, b times d. Well, if that's the case, then look what this is. This actually is the definition of the product of the dot product of the vector u and the vector v, and that is equal to the magnitude of u times the magnitude of v times cosine theta. Now notice that this is actually one way that you can actually compute the dot product of u and v. This tells us that the dot product of u and v is going to be equal to the product of their magnitudes times the cosine of the angle between them. So that is a second way to compute the dot product. You can use this approach, and you can also use this approach. However, the implication that we particularly care about is that if you divide both sides by the magnitude of u times the magnitude of v, we have the result that we're looking for, that the cosine of theta is equal to the dot product of u and v divided by the magnitude of u times the magnitude of v. And that's pretty much how it's derived. Of course, what we're more interested in is how can we use this in a problem. Well, here you go. Here's a problem. We want to find the angle between the vectors u and v. Okay, well, the angle between the vectors u and v is determined by this equation, cosine theta is equal to the dot product of u and v, u dot v, divided by their magnitudes. Or we can say that the angle is the arc cosine of that particular ratio. Okay, so the first thing I want to do is find the dot product of u and v. So u dot v, that's going to be equal to the product of their first components, which is going to be 5 times 4, plus the product of their second components, which is going to be negative 12 times 3. And that will give us 20 minus 36, which is equal to negative 16. Okay, now we need to find the magnitude of u. Well, that is going to be the square root of the square of the first component, which is 25, plus the square of the second component, which is 144. That is going to be equal to the square root of 169, which is equal to 13. Okay, and then the magnitude of v, that's going to be equal to the square root of the first component. The first component is 4. It's the square root of the square of the first component. The first component is 4. 4 squared is 16. Plus the square of the second component. The second component is 3. Square root is 9. That becomes the square root of 25. And that is equal to 5. So we're going to have that the cosine of theta is equal to the dot product, which is negative 16, divided by 13 times 5, and that will give us negative 16 divided by 65. If that's the case, then theta is going to be equal to the arc cosine of negative 16 divided by 65, and that will give us the angle 104.25 degrees, 104 and a quarter, and to the nearest decimal place that will round up to 104.3 degrees. And that is all I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing